These are the answers to the AP Chemistry packet on topics 5.4 to 5.11. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. Question 1 says, a proposed mechanism for a chemical reaction is represented above. Which of the following gives the correct expression for the rate law for step 1 of this mechanism? So this question relates to topic 5.4, elementary reactions, and here is one of the essential knowledge statements from the AP Chemistry course and exam description. The rate law of an elementary reaction can be inferred from the stoichiometry of the molecules participating in a collision. So all we need to do is focus on step 1, not the overall reaction, not step 2, just step 1. And then we have to count the number of molecules of each reactant. So I see one molecule of NO, or nitrogen monoxide, and I see one molecule of Cl2, or diatomic chlorine. So therefore, the rate law for step 1 of this mechanism, which is an elementary step, would be rate equals K times the concentration of NO times the concentration of Cl2. In other words, it's first order with respect to NO and first order with respect to Cl2 because there's exactly one of each of these molecules featured as reactants in the elementary step 1. So the correct answer to question 1 is choice A, rate equals K times concentration of NO times concentration of Cl2. Now let's take a look at question 2. Question 2 says the elementary reaction between NO3 and CO is represented by the equation above. Which of the following orientations of collision between NO3 and CO is most likely to be effective? So this question relates to topic 5.5, collision model. And here are a couple essential knowledge statements from the AP Chemistry course and exam description. For an elementary reaction to successfully produce products, reactants must successfully collide to initiate bond-breaking and bond-making events. In most reactions, only a small fraction of the collisions leads to a reaction. Successful collisions have both sufficient energy to overcome energy barriers and orientations that allow the bonds to rearrange in the required manner. So in this question, it's not about the energy, it's about the proper orientation of the molecules when they collide to form a particular bond. So we can see that on the left side of the equation, we have the molecule CO, or carbon monoxide, and on the right side of the equation, we have the molecule CO2, or carbon dioxide. So we have CO, the reactant, being transformed into CO2, the product. That means that in order for this collision to be successful, a new bond must be formed between an atom of carbon and an atom of oxygen. And so that's what we're looking for among the 4 choices in question 2. Is an atom of carbon going to collide with an atom of oxygen to form that new bond? And so the best choice that would show the fact that a new bond is formed between an atom of carbon and an atom of oxygen is choice B. We can see that the carbon atom is about to collide with an oxygen atom, and that would initiate that bond-forming event. So the correct answer to question 2, based on the orientation of the collisions and the new bond that would be formed, is choice B. Now let's take a look at question 3. Question 3 says, which of the following best helps explain why an increase in temperature increases the rate of a chemical reaction? On this next slide, you'll see something that I had presented in my video for topics 5.4 to 5.11. Now we see 2 curves that are changing as the temperature of the sample is increasing. On the left, we see a simple representation of the Maxwell-Boltzmann distribution of the speed, or the energy, of the particles. And the curve or the diagram on the right, in addition to showing how that is changing, we see a vertical line represented by that dashed line. That dashed line represents the activation energy for the reaction. And so in general, as the temperature of a sample increases, the average kinetic energy of the particles increases. The Maxwell-Boltzmann distribution curve becomes broader and flatter. And as a result of this change, a greater fraction of the collisions between the reactant particles will have enough energy to overcome the activation energy barrier. So you can see that that shaded portion to the right of the activation energy in that diagram on the right is increasing. That shaded portion means that a greater fraction of those collisions have enough energy to overcome the activation energy barrier. But we are not changing the activation energy. So that dashed line is not moving at all when the temperature increases. So on this next slide, I just remind you of that fact. At the bottom of this slide, it says, it is important to know that if you change the temperature at which a reaction is carried out, this will not change the magnitude of the activation energy for the reaction. So this slide also was from that video for topics 5.4 to 5.11. Now, back to question 3. Since we know that the increase in temperature does not affect the activation energy, we can eliminate choices A and B, which talks about having a lower or a higher activation energy. Now, taking a look at choice C, I'll remind you of something I had presented earlier in this video talking about the collision model. In most reactions, only a small fraction of the collisions leads to a reaction, and that's at any temperature. So here it says at higher temperatures, every collision results in the formation of a product, and that's not true. Only a relatively small fraction of the collisions will be successful. So the correct answer to question 3 that would best help explain why an increase in temperature increases the rate of a chemical reaction is the fact that at higher temperatures, high energy collisions happen more frequently. So correct answer is D. Now let's take a look at question 4. Question 4 says, hydrogen chloride, HCl, is formed from the elements hydrogen and chlorine as represented by the equation above. Which of the following diagrams shows the correctly labeled activation energy for the reaction between hydrogen and chlorine to form HCl? Even though this question does fall under topic 5.6, reaction energy diagrams, there's also a little bit of information that is in Unit 6, thermodynamics, that I'd like to mention. So the first thing I'd like to mention is that to the right of this equation, we can see that the delta H, or the change in enthalpy for this reaction, is negative. It's negative 185 kilojoules per mole of reaction. So knowing that the change in enthalpy can be either positive if it's an endothermic process, or negative if it's an exothermic process, that falls under topic 6.6, Introduction to Enthalpy of Reaction. I just wanted to mention that part about the negative delta H means it's exothermic. Also in Unit 6 is topic 6.2, energy diagrams. And we can see on this slide that if the potential energy of the products is higher than that of the reactants, then energy is absorbed and the reaction is classified as endothermic. On the other hand, if the potential energy of the products is lower than that of the reactants, we say that energy is released and the reaction is classified as exothermic. So those two topics, topic 6.6 and topic 6.2, would be relevant when analyzing the 4 choices in question 4. Let's go ahead and eliminate the 2 energy diagrams that are actually classified as endothermic, because we know that this reaction has a negative delta H and is classified as exothermic. Let's eliminate choice A, because that diagram shows an endothermic process. And let's also eliminate choice B for the same reason. The diagram shows that that process would be classified as endothermic. Now, how do we label correctly the activation energy? Well, this does fall under topic 5.6, reaction energy profile. The energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. And the energy difference between the reactants and the transition state is the activation energy for the forward reaction. So on this next slide was something I had presented in my video for topics 5.4 to 5.11. And one of the instructions on this slide was to draw a vertical arrow to indicate the magnitude of the activation energy for the reaction. And it would be from the level of where the reactants start on the potential energy diagram to that transition state, which is the maximum energy value. Now, back to question 4, and we can see that the correct answer to question 4 is choice C, showing the difference in energy from where the reactants start to the top of that transition state. So choice D is incorrect because that is showing the change in energy for the overall reaction. So the correct answer to question 4 is choice C. Now let's take a look at question 5. Question 5 says the two mechanisms in the table below have been proposed for the reaction represented above. Which of the following observations would support mechanism 1 but not mechanism 2? This question relates to topic 5.8, reaction mechanism and rate law. And the essential knowledge statement says, for reaction mechanisms in which each elementary step is irreversible, or in which the first step is rate limiting, the rate law of the reaction is set by the molecularity of the slowest elementary step, that is, the rate limiting step. So the word molecularity simply means we have to count the number of each reactant particle which would relate to the order with respect to that substance in the rate law. So for mechanism 1, let's focus on the slow step, and that would be step 1. And in step 1, I see 2 particles of X that appear as reactants in that slow rate determining step. So based on the molecularity of that step, it means that that rate law would be second order with respect to X because there are 2 particles of X that appear as reactants. Again, in the slow rate determining step, I'm only working on the slow step. I'm not looking at the fast step. Now for mechanism 2, the first step is also the slow step, but this time, instead of 2 particles of X, I see 1 particle of X and 1 particle of Y2 that appear as reactants in that slow rate determining step. So the rate law for mechanism 2 is different than the rate law for mechanism 1. The rate law for mechanism 2 would be first order with respect to X and first order with respect to Y2. Again, based on the molecularity, there's 1 particle of each, so first order with respect to each substance. Now, overall, the order of each rate law would be second order. Back in topic 5.2, Introduction to Rate Law, we learned that the sum of the powers of the reactant concentrations in the rate law is the overall order. So 1 plus 1 is 2. Each of these rate laws is second order overall. Now back to the choices in question 5. I'm looking for an observation that would support mechanism 1, but not mechanism 2. And since each of these rate laws is second order overall, we can eliminate choice D. That's not unique to mechanism 1 only. And we don't have any information that would suggest energy is absorbed or released, so saying that the reaction is exothermic, that's not relevant to the comparison that we're making here. It has to do with the rate law. So the rate law for mechanism 1, based on the slow step, would be second order with respect to X, and the rate law for mechanism 2, based on the slow step, would be first order with respect to X and first order with respect to Y2. So there's the difference between the two mechanisms. Mechanism 1 does not feature any concentration of the substance Y2, so the reaction rate if it's independent of substance Y2, then that would support mechanism 1, which does not feature Y2 at all in the rate law. But it would not support mechanism 2 because substance Y2 is in fact included in that rate law. So the absence of substance Y2 from the rate law would be something unique to mechanism 1, but not mechanism 2. So the correct answer to question 5 is choice B. Now let's take a look at question 6. Question 6 says, the following reaction mechanism is proposed for the decomposition of H2O2, hydrogen peroxide. Which of the following choices has correctly identified a species that behaves as a catalyst and a species that behaves as an intermediate in the proposed mechanism? So back in my video for topics 5.4 to 5.11, I taught that an intermediate is a substance that is formed as a product in an earlier step of a mechanism and then consumed as a reactant in a later step of the mechanism. So on this slide, we can see that the substance NO3 is formed as a product in step 1 and then also consumed as a reactant in step 2. So NO3 would be classified as an intermediate in this particular mechanism. Now, in that video, I also taught that a catalyst is a substance that is consumed as a reactant in the first step of a mechanism and then formed as a product in a later step of the mechanism. So on this slide, we can see that the substance Cl is consumed as a reactant in step 1 and then formed as a product in step 2. So the Cl would be classified as a catalyst in this particular mechanism. Now, let's go back to question 6 so we can see that there is a substance on the right side of the equation in step 1. This is called the hypoiodite ion, which has the formula OI-, and that is formed as a product in step 1 and then consumed as a reactant in step 2. So the hypoiodite ion, or OI-, is classified as an intermediate. And then I see the iodide ion, or I-, is consumed as a reactant in step 1, and then iodide, or I-, is formed as a product in step 2. So in this mechanism, the iodide ion is classified as a catalyst. So now we can answer question 6. So the correct answer to question 6 is choice C. Iodide, or I-, behaves as a catalyst. It is consumed as a reactant and then formed as a product, whereas the hypoiodite ion, or OI-, is an intermediate because it's formed as a product and then later consumed as a reactant. So again, the correct answer to question 6 is choice C. Now let's take a look at question 7. In question 7, it says, the rate law for the reaction represented by the equation above is rate equals K times concentration of NO2 times concentration of F2. Which of the following could be the first elementary step of a two-step mechanism for the reaction if the first step is slow and the second step is fast? So we're looking at topic 5.8, reaction mechanism and rate law. And again, we're focusing on the molecularity of that slow rate determining step. So the fact that we have a rate law that contains first order with respect to two different chemicals, we need there to be one particle of each of these chemicals so that the number of particles, the molecularity, matches the order in the rate law. So in that slow step, the first step, there should be one particle of NO2 and one particle of F2 that appear as reactants. So the correct answer to question 7 is choice B, because it's the only choice that features exactly one particle of NO2 and one particle of F2, and then that matches the order in the rate law for that slow rate determining step. Now let's take a look at question 8. In question 8, it says a reaction and its experimentally determined rate law are represented above. A chemist proposes two different possible mechanisms for the reaction, which are given below. Based on the information above, which of the following is true? Let's focus our attention on that first slow step, the slow rate determining step, and look at the molecularity or the number of particles that appear as reactants. So for mechanism 1, I only see one particle of X2 as a reactant in that slow step, so that rate law would be first order with respect to substance X2. Now for mechanism 2, I see that the first step is also the slow step, but again, there's only one molecule of substance X2, so that rate law would also be first order with respect to substance X2. So these two mechanisms are not exactly the same in terms of their steps. However, the first step features exactly one molecule of X2, and that is the slow rate determining step. So the rate laws are identical and they match the experimentally determined rate law that we were given in this question. So the correct answer to question 8 is choice C. Both mechanism 1 and mechanism 2 are consistent with the experimentally determined rate law. Now let's take a look at question 9. In question 9, it says, the experimental rate law for the reaction represented above is rate equals K times the concentration of substance D2 times the concentration of substance QX squared. So that rate law tells us that it's first order with respect to D2 and second order with respect to QX. And the question asks, which of the following proposed mechanisms is consistent with the rate law? Let's start with choice A. In this mechanism, the first step is the slow rate determining step. So all we have to do is count the number of reactant particles in that slow step. And I see 2 particles of QX that are featured as reactants in that slow rate determining step. So the rate law for the mechanism in choice A would be rate equals K times concentration of QX squared. In other words, second order with respect to QX. Now, since that rate law does not match the experimental rate law that we were given in this question, we can eliminate choice A. Now, the next mechanism I'm going to take a look at is actually choice D. And the reason I want to focus on choice D is that in that mechanism, the first step is a fast equilibrium, and the second step is the slow rate determining step. So this falls under topic 5.9 in the AP Chemistry course and exam description. And so topic 5.9, steady state approximation, deals with situations where the first step is actually a fast equilibrium, and then the second step of the mechanism is the slow step. What I'm going to present on the next few slides is a strategy that I had presented in a video for topics 5.4 to 5.11. So we're going to focus on a general strategy for determining the rate law of a reaction when the second step in the mechanism is the slow step, and the first step is a fast equilibrium. So I have identified on this slide a step 2, which is the slow rate determining step, and now I'm going to write the rate law for step 2, the slow step of the mechanism. It would be first order with respect to the substance NOBr2, and first order with respect to the substance NO, because there's one particle of each of those substances that appear as reactants in that slow step. Now, here comes the issue that we need to do a substitution procedure, because if the rate law that we just wrote for step 2 contains a substance that is an intermediate, we need to replace it. An intermediate is a substance whose initial concentration is unknown, and therefore it cannot appear in the rate law for the overall reaction. So we need to replace or substitute the NOBr2, which happens to be an intermediate in this particular mechanism. So if step 1 is a fast equilibrium, then the rate of the forward reaction is equal to the rate of the reverse reaction. And now that I've written that the rate of the forward reaction, which would be K times concentration of NO times concentration of Br2 is equal to the rate of the reverse reaction, which would be K times concentration of NOBr2. That's the substance that I'm trying to get rid of in the rate law. It's the NOBr2. I need to substitute for that. So the equation that I wrote can now be rearranged and then used to write an expression that defines the intermediate so that you can replace it in the rate law. So now that I have written an expression that defines the concentration of the intermediate, NOBr2, in terms of the other substances, NO and Br2, I can do that substitution procedure. And once I do that substitution, I now have a rate law that only features the reactants in this equation and does not feature an intermediate. So the final version of the rate law after that substitution procedure has been done does not contain the intermediate. Again, this is topic 5.9, steady state approximation, where the first step is a fast equilibrium and the second step is the slow rate determining step. Now that I've walked you through the general strategy for determining the rate law in this type of situation, let's go back to that mechanism in choice D and use that same procedure. So step 1 in this mechanism is a fast equilibrium, and step 2 is the slow rate determining step. So we'll start by writing the rate law for that slow step, step 2, and I see one particle of D2 and one particle of Q2X2. So this rate law shows its first order with respect to D2 and first order with respect to Q2X2. Now that is the substance that's the problem. Q2X2 is actually an intermediate, and now we need to replace Q2X2. So I'm going to go ahead and write the equation for step 1, which is that rapid equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. So K1 times the concentration of Qx squared for the forward reaction from left to right is equal to K minus 1 times the concentration of Q2X2 for the reverse reaction. Here comes the substitution part of this procedure. So I need to eliminate the intermediate. So I've written an expression that defines the concentration of Q2X2 in terms of the reactant, Qx. Here comes the substitution, and now my final version of the rate law looks like this. Rate equals K times concentration of D2 times concentration of Qx squared. Now this rate law not only does not contain the intermediate, therefore that was successful in getting rid of that intermediate, it also matches the rate law that we were given in question 9. So the experimental rate law for the reaction is rate equals K times concentration of D2 times concentration of Qx squared. So this is proof that choice D is the correct answer. Now if you're watching this video, you might be thinking, well, what about looking at the mechanisms for choices B and C? Well, it's very rare in AP chemistry that the third step in the mechanism would be the slow step. Very complicated procedure for trying to write a rate law when step 3 is the slow step. So what we typically see in AP chemistry is either something like choice A, where the first step of the mechanism is the slow step, or we see something like we saw in choice D, which falls under topic 5.9, where the first step is a rapid equilibrium and the second step is the slow step. So in that procedure, to substitute for the intermediate, I have shown you that choice D is in fact the correct answer to this question. Now let's take a look at question 10. In question 10, it says, when free chlorine atoms encounter O3 or ozone molecules in the upper atmosphere, the following reaction mechanism is proposed to occur. We see that step 1 is the slow step, step 2 is the fast step, and the question asks, which of the following reaction energy profiles best corresponds to the proposed mechanism? So this question falls under topic 5.10, multi-step reaction energy profile, knowledge of the energetics of each elementary reaction in a mechanism allows for the construction of an energy profile for a multi-step reaction. It also relates to topic 5.6, reaction energy profile. So here on this next slide is a question that I had presented in my video for topics 5.4 to 5.11. We see two diagrams, and the question says, which diagram, number 1 or number 2, represents a reaction that should occur at a faster rate? Justify your answer. Let's focus on the activation energy for these two diagrams. So I see a smaller activation energy for diagram 1, and I see a larger activation energy for diagram 2. So a higher magnitude for the activation energy is associated with a slower reaction rate, and then vice versa, a lower magnitude for the activation energy is associated with a faster reaction rate. So diagram 1 represents a reaction that should occur at a faster rate because it has a smaller activation energy. Now, back to this question. It is a slow step for step 1 and a fast step for step 2 in this mechanism. Since step 1 is the slow step, it should have a higher activation energy barrier. And since step 2 is the fast step, it should have a lower activation energy barrier. So the correct diagram that would represent this situation is choice B. We can see a higher activation energy for step 1 in that diagram and a lower activation energy for step 2. So it's going to be a slow step followed by a fast step. So choice B is the correct answer to question 10. Now let's take a look at question 11. In question 11, it says, the potential energy diagram for the uncatalyzed decomposition of X2Y2 is shown above. Which of the following best represents the energy diagram for the decomposition of X2Y2 in the presence of a suitable catalyst shown as a dashed line? So this question falls under topic 5.11, catalysis. Some catalysts accelerate a reaction by binding to the reactants. The reactants are either oriented more favorably or react with a lower activation energy. So that's the important point. It's going to be a lower activation energy. So on this slide, which I had presented in the earlier video for topics 5.4 to 5.11, I showed what can happen if the activation energy is lowered, and you can see that vertical dashed line is moving from right to left. So the presence of a catalyst can provide an alternate reaction pathway that has a lower activation energy. And if the activation energy decreases, then there should be a greater fraction of collisions between reactant particles that have enough energy to overcome the activation energy barrier, and this results in a faster reaction rate. Important information about catalysts. The presence of a catalyst increases the reaction rate by providing an alternate reaction pathway with a lower activation energy. Adding a catalyst to the reaction mixture does not change the temperature at which the reaction is carried out. And a catalyst does not change the potential energy values for either the reactants or the products. The difference in energy between the products and the reactants will remain the same. So on this next slide was a question I had presented in that earlier video, and it says, in the energy diagram above, which reaction pathway represents a reaction that occurs in the presence of a catalyst? Justify your answer. So the solid line represents the uncatalyzed reaction pathway with a higher activation energy, and the dashed line represents the catalyzed reaction pathway with a lower activation energy. Now, the difference between the reactants and the products has not changed in terms of this energy diagram. That's an important point. Let's go ahead and take a look at the 4 choices for question 11. We're looking for the energy diagram for the reaction in the presence of a catalyst shown as a dashed line. The first thing I'm going to do is eliminate choices A and C, because a catalyst does not change the potential energy values for either the reactants or the products. So choice A and choice C have shifted the entire dashed line higher or lower than the original, but a catalyst is not going to change the potential energy values for the reactants or the products. Since the presence of a catalyst increases the reaction rate by providing an alternate reaction pathway with a lower activation energy, that makes the best choice choice B for question 11. So choice B is the correct answer with a lower activation energy pathway in the presence of a catalyst. Now, since question 11 is the last question in this packet, then I hope that you found all of these answers and explanations helpful. Thanks for watching.